各位同学的到来啊。那么今天呢，是我们邀请了PIFI 的访问学者，就中国科学院PIFI访问学者，来给我们那个是 Gutsev 给我们做一个报告。那报告的题目呢，就是 Theory meets experiments, joint insights into perovskite passivation strategy. Let me introduce Professor Gutsev Lavlente. 这个 Gutsev Lavlente 博士，他是来自俄罗斯科学院化学物理问题研究所，现在更名为俄罗斯科学院联邦化学物理与药物化学问题研究中心结构化学实验室助理教授。他主要是负责呢材料的地性原理计算。近年来呢，主要是和知名的学者PAVL还有这个Aldashan院士那个合作开展研究，尤其是在钙钛矿太阳电池材料及界面的稳定性方面，做出了许多创新性的工作。近5年来呢，在 AFM 等国际期刊发表高质量论文40余篇。那么下面就有請Gutsev Lavlente 博士给我们做報告，請大家歡迎。
Thank you for the multilingual introduction. Very pleasant to be here. Thank you for organizing this on such short notice. So the whole purpose of this, is it recording?
Yes.
Okay, great. The whole purpose of this presentation is basically to demonstrate to you and explain to you what is the role of theory in our work. So basically, how does theory meet experiment? How does this collaboration actually happen? And of course, the central point of this presentation is our collaboration, which is international collaboration between Russia and China. So the main results of this collaboration are actually quite impressive considering the short time period that's passed. So personally, I've been Presidential International Fellowship Initiative recipient, so fellow from the sponsored by the Chinese Academy of Sciences, and the host is Dr. Xu. And I've received it 3 times, which is great, and I'm really thankful to the Chinese government for such an opportunity. Also, we started this collaboration with Memorandum of Understanding that we'll probably update. Obviously, they're usually signed for 3 years, so we expect 3 more years. We expect a continuation, basically. Finally, we won very recently a joint grant between the Russian Science Foundation and the Chinese Science Foundation. It's called the Smart Passivation approach, the key to reaching record high efficiency and stability of perovskite solar cells. So this is essentially a continuation of the work that I'll be presenting here. So yeah, it's a very, very good collaboration that we have going, and it's ongoing. So this is not the end, this is just a midpoint. So just discussing the results already achieved. And so here I've basically visually represented the collaboration. So the collaboration is one theoretician and a very large and talented group of experimental scientists with Dr. Xu leading them. And of course, we also get a lot of support from the Russian group in Russia. And so far we have 7 papers published, of which 6 are Q1, very impressive result. And 2 are in review, soon to be published, 3 in progress, and some more that are just starting. So next year, expect this more orange on the screen. There's going to be more. So the main goal of the collaboration is stabilizing interfaces via passivation. So in this report, when we mean passivation, we broadly mean the improvement of interfaces of perovskite grains or of perovskite charge transfer layer interfaces. But it can also actually mean perovskite grains, which is a topic that we haven't touched very much, but in literature it's actually quite, it's also a popular topic in literature. When we say good passivator, we mean that it can improve the photovoltaic efficiency and the stability of the device by first passivating the deleterious defects, which inhibit device performance and just degrade it in general. Improve charge extraction and/or the band alignment. So this will directly improve the power conversion efficiency, but it's actually quite a difficult thing to calculate. And here we will discuss both basically salts and organic molecules or organic salts. So there's to the left a general device. Many people already here are familiar with it. And basically the passivator will go either between the perovskite and the hole transport layer or the perovskite and the electron transport layer. That's the main goal. So the benefits of passivation, there's actually very many. Currently one of the big topics is how we protect it from water, because obviously a solar cell has to be outside, so it has to be protected from humidity and water. The device can better inhibit the movement of ions, because it's generally believed that this movement is actually deleterious. So in general, we really mean the iodine vacancies of the interstitial iodines. And it's notable that there's experimental evidence that these can get all the way to the electrode. So the perovskite is actually very corrosive, is what can be said about this, is that it's actually very difficult to do this. It's actually a very challenging topic, which is why so many people are at work, obviously. So the device can become flexible, which is really cool. It opens up very many new applications which are not available to silicon-based cells. And well-stabilized device, we can make it thinner, thus semi-transparent, thus we can put it on buildings. Buildings are a big source of global warming and CO2 output, so actually pretty important. And the final thing is, space is the final frontier. It's even possible to make them stable in space. And actually in space, they're sometimes even more stable than in terrestrial conditions. And this has to do with radiation hardness. It turns out they're more hard than silicon, which is impressive. So what can DFT do for us? It can calculate the work function and how the work function changes. And we always compare to pristine. So pristine, on the right-hand side here, you can see the vacuum is in the orange area. The perovskite itself is the gray area. And we make determinations symmetric. And this is very important, because now we can see how the vacuum changes by introducing asymmetry. So by asymmetry, we mean the dipole moments. A big topic in this field. We can do the molecular electrostatic potentials, the dipole moments, the topological descriptions, and I'll cover that much later in this presentation. We can have surface charge transfer and charge displacement. So the passivator can displace the charge in the perovskite, basically induce the dipole. Absorption energy of the formadium iodide-rich surface, we mostly consider formadium lead iodide. So basically in the experiment they're slightly mixed, but in theory we just consider the pure case, so the alpha phase, the black phase. And finally, we can also do the PBI2 rich surface. We can do the chemical descriptors, so this is Gaussian, typically we calculate. Now we can do electronegativity, chemical hardness, electron affinity, basis, observables. These are currently also very popular in literature. This final topic I'll have to leave for next time, but we can also do non-adiabatic molecular dynamics. So this is involves non-radiative. Non-radiative recombination is what it means, but it's not limited to just non-radiative recombination. This gets into the very, very modern and new topic of hot carriers, because hot carriers are probably the future. If we can engineer the devices to take advantage of hot carriers, we can break the SQ limit. So this is huge. And here we can do both. We can do non-radiant recombination rates and hot carrier cooling rates. And I found that you can actually do the same at the same time, but it does take a lot of computer time and a lot of space. So each calculation is like 2 terabytes. It's actually very challenging. But also means that it's hard for other people to compete with us, so it's a good moat, so to speak, around our research. Point 1, right? So when we talk about work function change, see, when we introduce an iodine vacancy, the work function shifts. So the potential in space shifts in the vacuum space, shifts downwards. And this is, when we see this, we know it's a whole acceptor. When it shifts, when it's sloped upwards, it's an electron acceptor. So actually very convenient. So at a glance, we know a lot already about any kind of passivation we do. So we can compare for basically any passivant to any other passivant just at a glance. And that's cool. So absorption energies of salts. In literature, this is actually a painful topic because it must be done rationally. So there's 2 types of surfaces generally considered. So we're considering the 100 surface because an XRD is the most well-represented surface type by far. So we get the PBI2-rich surface, which is more N-type, and the formidinium iodide-rich surface, which is more P-type. And to the left here, you can see the 2 types. So this is PBI2-rich, and this is formidinium iodide-rich. So you can see this is basically a bare surface, whereas this kind of mixes into the surface. So quite different, actually. And you can see that the sulfonates can just do the same but in reverse. So also interesting. This research we started with sulfonates, but we mostly done amines. The charge balance must be retained. Very important point, which I'll explain in the next slides. Neutral passivants also considered like melamine and also cytosine. So the formidinium iodine-rich surface, you can see that, for example, we can take our anion and replace the surface-based iodine with it. So basically, we're filling a iodine vacancy here. Later's not so strong, so yeah. Iodine vacancy. In the central one, we can do a formidinium vacancy. So here we put a charged donor in there, so the amine. And finally, we can do a Schottky, we can fill a Schottky defect. So this is when we put in the whole salt into the vacancy. And this is actually, they're common. These are actually common. I'll explain later. So this is actually a very good model for the real world device. For the PBI2 surface, this is where people usually make mistakes. For example, you can't just add your anion to the bare surface because it's charged unbalanced. If you have a anti-side defect of PB in place of I, when you think about it, PB is +2, I is -1, so now we have a +1 surface. So yeah, we can add an anion there, -1, we balance out the charge. If we add the salt as is, that's fine. But to the anti-side defect, we can't do that because again, we get charge disbalance. And this is all very important because there are many mistakes in literature. And if there's a mistake in literature, we can't compare literature, not bad. So this is the first topic I'd like to talk about is PFPACl and TFPACl, and that's basically where we have basically a chain, a carbon chain, short carbon chain, propyl group, and we fluorinate the tip there, so the CH3 becomes CF3, and for the PFPA, we fluorinate the next carbon, so we get 5 fluorines. And this is a PIN device, and the cool thing here is that, first of all, when it's bent, when it goes through a bunch of bending cycles, it remains pretty stable, which is great. Another thing is, over the time, they consider 1,000 hours, it stabilized quite well compared to the pristine material, to the unpassivated material. Okay, but this is, for Fury, this is kind of the big story. For Fury, if we look in literature, we know that dipole and work function shift are related, as I told you before. But what's more so interesting is that they this is what they're passiving, this perovskite HTL interface. And from passivation, we induce charge accumulation at the other side of the perovskite. And this, other semiconductors can't do this. It's actually a very polarizable material, so polarizable that it can polarize for like hundreds of nanometers, which is nuts actually. And the thing they passivated with was octylamine plus some counter anion. So basically they checked out what the difference is and when they varied the counter anion. So this is tosylate, and then this one they did just iodine. So in the case of iodine, we get the bad result of accumulating charge at both interfaces. With the tosylate, the problem is not so big. So we don't want negative charge at the HTL perovskite interface, obviously, because that will cause problems. So the big point is check out how deep the dipole is propagated to the perovskite. So the whole wafer, that's pretty unusual. So what can we compare to experiments? It's a little bit challenging actually. So here you can see the absorption energies for all the cases I described before where the charge is reasonable. So all the reasonable cases I'm considering, you can see it varies from like nearly -7 EV, so very strong, and then in other cases less than 1, so pretty weak. And then we also look at the work function change, and you can see, so this is the forbidding iodine-rich surface, so it shifts the work function up in that case, and on the other surface it shifts it down. And we know from experiment that it's actually shifted down. So how do we explain this? Well, for the first case, which is probably more likely because this is the HTL perovskite case, we're actually passivating the Schottky defect. And the Schottky defect is actually plus 0.12 eV. So we compare here to pristine, we should be comparing to the Schottky. And when we do this, actually the shift is negative. So as we're healing the defect, our work function is going down. But when you compare it to pristine material, it looks like it's going up, so it's a complicated thing. PBI2, we're not, in the PBI2 case, we're not really concerned about Schottky defects so much. So the fact that it shifts it down seems okay also. So as I've just told you, the data interpretation is quite complex, even though it should seem easy. We just passivate the surface, look at the work function change, and see does it go up or does it go down. But it's not so simple. The other thing is the work function changes over time, and I'll show you this. So this is 2 picoseconds, a pretty substantial amount of time. And you can see that when we go from the peak to trough, we get like a difference of 0.4 eV in the conduction band minimum, which for a semiconductor is unusual. And you can see that the band gap has almost 1/10 standard deviation EV. That's a lot. So let's look at the chemical observables. So the chemical observables, 4 of them are calculated. The green one is from the experiment, just for reference. So this is chemical hardness, this is electronegativity. So when we look at the lithium cation affinity donor number, these are basicity observables. This is uncoordinated, this is coordinated. They're both higher for TFPA, which is good because our pK goes up and our basicity observables go up. So everything's fine, everything's correct. So we know that PFPA is more electronegative and chemically harder, so we expect it to dissociate more and thus be more available to passivate the surface. So that's probably one of the reasons why it's better, somewhat better. And this is good because we have many Schottky defects to passivate, and this is the big paper. It's been cited almost 800 times. It's a pure DFT paper, but the defect formation energy of the Schottky defect is so low that the expected concentrations are huge. So very many. But they're also not deleterious, which is interesting because they're charge balanced. But on the surface, it might be a bit different story. Surface is different. For bulk, it's definitely not bad. Surface, different story. Okay, and these graphs are really cool. So this, when we put on the passivant, the charge is displaced, so we get an induced dipole. but it's not a uniformly induced dipole. It's it kind of it goes in a sinusoidal pattern, and then at the very, very end we see a tail, just like an experiment actually. So very interesting. So we do get an oscillating thing going on, and at the very end we get a tail, and that's how we get the induced dipole. And this is the 2D case. So the same material, it's the same data, just different dimensionalities. This is a 2D, and this is the 1D. 1D is actually a little bit easier to interpret, which is, I kind of prefer these for interpretation and these for figures, because they look cooler. So let's just analyze the tail more, because it's actually not so simple to think about. So the tail, I mean, this is only like 3 nanometers, so we can't directly compare it to experiment, but it looks a lot like this thing. So this result, as I said before, is unusual for a semiconductor. How is charge being propagated so deep into the perovskite? The reason is perovskites have high dielectric constants and low exciton binding energies, and they're actually very high polarizable, so it checks out, and the experiment also checks out. So this is reasonable. This result is okay. We'll do this. This result in general is fine. This is probably pretty close to experiment. But what if I did some more calculation later, and so we know that PFP is stable for 1,000 hours, and it's better for bending benchmarks, etc. But we have some unpublished calculations regarding the whole coupled Frankel oxidation, and it shows that TFP is actually more stable. So over a long period of time and under intense illumination, we do predict that TFP will be better, which is unusual, but that's just the theoretical fact. For now, we don't have experimental data, it's simply a prediction. Okay, another interesting case is Benzocaine Chloride, and here we're considering a NIP device, so the polarity of our displacement diagrams changes. Now the ETL is up here and the HTL is down here. Okay, so again, the displacement diagrams are similar, and here's the benzocaine. The big thing here is, if you look at various calculations, you can see that the work function, the absorption energy in the work function actually varies quite a bit between various cases. But in general, it's negative, and in experiments also negative, so that checks out. It does agree with experiments. But the caveat is that these changes will be much less for the formidinium iodine rich surface. So we don't expect such big changes for the other surface. And the cool thing here is we can look at the HOMO and LUMO and just see what Passivation does. In this case, we see that for the surface, unpassivated but pristine, we see that the HOMO, the valence band maximum, localizes inside the bulk, which is interesting. And the conduction band minimum is delocalized. For the passivated case, the valence band is the same, but the conduction band shows that the electron will actually somewhat localize at the passivator, so that's probably good for charge extraction. So this needs to be investigated more, but this is a very promising result actually. Also unpublished still, so there's plenty of unpublished data that's very interesting. Okay, this is an ongoing project. I based Binyam and me are writing it. He's doing the SCAPS 1D calculations. I did the DFT calculations. DFT calculations basically compile all the data we did together into a summary kind of work, but also we did a lot of new calculations. So you can see that the sulfonates actually passivate perovskite much better than the amines. So that's interesting. So they bind stronger, but there's probably some kind of threshold above which we need binding strength. So excessive binding strength might not necessarily be a good thing. So just because it's bigger doesn't mean it's better. But just because it's stronger doesn't mean it's better. So that's just something to keep in mind. There's other results here. I'm just not going to prove them, but a lot of interesting patterns emerge. The other thing is we want to think about how the 2D 3D interface is engineered. So You know, when we add PEAI to the surface, we get a 2D type of perovskite at the surface. And we want to think about how do we control this. So the idea was, why don't we change the iodine to something else? And by changing the iodine to something else, we use different types of acids, and they have different acidity, right? So generally, hydroiodic acid is not generally always very strong acid. Then HTFA is almost a strong acid, and acetic acid is, of course, a known weak acid. And a known weak acid means that it doesn't dissociate easily, and that's what we write here, is that the interaction strength is stronger for, so basically the way it's projected is, this is the iodine-based one, and all the way down here we have the acetic-based one. And in this case, we don't get 2D perovskite, so in this one, when we use this passivator, no more 2D. This one, we, of course, well known 2D. So as our acidity goes down, our 2D phase also disappears. That's the result. And that's the result we needed to simulate. The literature is already quite good on this in terms of studying the 2D stuff. It's already known that the binding of the 2D phase, so the binding of basically this piece to this piece is what means by the binding energy. As it goes down, as it becomes stronger in binding strength, the 2D phase becomes more stable. So DFT actually predicts the stability pretty well. This paper demonstrated that very well. And fortunately, our results are in agreement with experiments and previous papers. You can see that in this case, the iodine-based one binds the strongest when we look at the binding strength. The TFA one is intermediate, binds somewhat strong, still stable and not as stable. And the one based on acetic acid, not stable at all. So, experiment and here we are in agreement. The other thing to think about is just to look at it, what's different between the iodine-based one and the acetic-based one. You can see that the potential in the middle here actually decreases, and I'll show you in the next slide what that means. So basically, in this area between the passivants, so when we make a 2D phase, we have passivant on one side, passivant on the other side, and the passivants meet. And when the passivants meet, we get a band of negative charge. So that's where holes will be attracted here, probably. And why does PEAI, why is it more stable? Well, when you look at it, it's slightly more crooked, so it shifts a little bit. And by shifting a little bit, it optimizes the T interactions. And apparently, TFA and AC don't have as much freedom to shift, so they stay more linear, and thus not as stable. And the acetic-based one is the most linear. And you can see that when it's very, very linear, it actually starts to displace charge throughout the perovskite. And this is a very interesting result, to be honest, and also, again, warrants some more investigation, so lots of things to think about here. So acetic acid creates a strong charge disturbance in the perovskite lattice, and the other one's still interesting. We can also do the binding energy of the counter anion, and this is not so easy because you have to work with chemical potential. So you have to go to boundary conditions, you have to calculate the phases. I won't go into too much detail, but basically I made up some new boundary conditions to make sure I can compare directly the iodine to the acetic acid and TFA. So that's the whole point of this slide. And yeah, when we look at the result is, you can see that depending on the chemical potential, our absorption energy is changed by like almost 1 eV, which it's a pretty big change. But in general, we see the iodine and the TFA have similar binding strengths. Acetic acid is weak relative to this is currently unpublished, but we know that PEA is actually chemically active, and it can actually do some reactions. So for example, if Fa loses a hydrogen, which it can do, it can attach. So we can have this reaction happen. So we lose that H free and we get this tail. So now we get PMA. instead. And that it has pretty different properties compared to just PEA. And just to say, this kind of calculation is kind of tough to do. So to get the transition state this well takes a lot of work. But from what I heard from Pavel, it seems like the energy, the transition state energy is comparable to experiments. So that's exciting. Also still unpublished. So final result is experiment indicates that this CDIC-based PEA does not yield 2D film, but instead it yields this PD acetate. And this apparently shifts the CBM a lot, so here it is. So in these cases, you see the conduction band is kind of high. In this case, it shifts way down. So if we wanted to do this in the future, how would we do it? So we would need a perovskite lead acetate interface, not very easy to construct. So how do we do it? Well, I'm glad you asked because it's topic of some other projects. So the strategies for building perovskite charge transfer layer interfaces is first of all the problem. The problem is there's way too many possibilities, like thousands. You consider all the Miller indice combinations, it's just too hard. We need a screening method. DFT is not going to do it. DFT is too expensive. There is a method to do it without DFT calculations. So this is a big data approach, actually. So what they do is, what we do, this is a method from the 1980s. So we find the reduced lattice vectors and for two corresponding Miller indices and find the minimum coincident interface area via the ZnO algorithm. So that's the algorithm. It was published in 1984. Actually, super useful algorithm. Okay. And now we just need to apply this algorithm thousands of times over a database. And that's what they can do in 1984. Now we can't. So that's kind of the big result. So here's the work process. We take the materials project database, gives us all we need. So that's the database we work with. We find the minimum coincident areas and we tabulate them. And then we use experimental data to think about it. So we just look at the XRDs. So for example, for perovskite, we consider 100, 110. And then for the other material, we also look at the XRDs again. For example, zinc oxide has many different phases that are stable, so we have to also consider different phases of zinc oxide and the XRDs of each one. But when we go through everything, we do have to personally look at it. So there is some human element involved. We don't just tabulate and just blindly follow it. But in the end, we can figure out which is the best interface and then construct it and calculate with DFT. And that way we don't calculate thousands of interfaces, we can calculate just a handful. And that's how we save a lot of time. Okay, this was a very early project a few years back. I was interested in mixed halide perovskites, so CSPBI2VR. And in this case, the big result is, that has to be the big result, and also the big problem, is that pores will accumulate in the iodine-rich part, and that will cause segregation, and DFT confirms this. The other thing we wanted to know is which phases can actually combine together for real. And what we found is black phases are all compatible, regardless of they're iodine-based or bromine-based. Yellow phases are all compatible, regardless. But yellow and black phases are never compatible. So the interfaces are always unstable. So when we have yellow and black phase, there has to be something in between to actually. So there's basically there's a sandwich and there's something in between the sandwich. So possibly it's like cesium iodide, for example, or there's other phases of cesium iodide, like cesium I4 if it's iodine rich. So here was a really impressive work by Pavel's student, now postdoc in Italy, Marina. She basically took half of the periodic table and doped it dilutely into perovskite. And then she analyzed the results. But the main result I'll tell you in a moment. But I'll just say that, yeah, we did a whole bunch of DFT as well. We found that the local geometry changes a lot with zinc, platinum, and iron. And then for erbium and europium, essentially doesn't change much at all, which is reasonable because they're big and lead is also large. So from a size perspective, it makes perfect sense. Then we did a lot of calculations like the defect formation energies, and then the defect transition energies. So we did a lot. This was a whole bunch of work. The main thing to say here is that no one else has ever done such a large sampling. No one has ever done so many metals at the same time. So that's the cool thing about this section. But the main result was not this. Even though this took a lot of time, this was not the main result. The main result is that mercury does not dope into the MAPI directly, but it stabilizes the MAPI the most. So stabilizes via passivation. So what is the passivator? So first of all, we thought maybe the passivator is something that's a perovskite-like, so MAHGI3, for example. So maybe it matches on with, so this was the idea that Marina came up with, and I had to check it. Immediately I went in, used the ZM model, and it found that it's unstable. Well, let's try it with DFT anyways. So we constructed DFT, and you can see the interface looks good, like the terminations look good, like visually looks good. But first of all, the mismatch is over 20% as the ZM model predicted, and ultimately DFT says it's unstable. So the ZM model is actually reliable to some degree, I suppose, but in this case it's very reliable. So we had to find an alternative explanation. We can't, the perovskite type like HG phase, no good. So we have some kind of intermediate layer. And the intermediate layer might be PBI2, HGI2, PB, HG, etc. What we found basically is 20 megabytes of possible interfaces. These are all tables, so it's a huge amount of data. So all we did is exclude this possibility and just say that the possibilities are very, very large, very many. Another time we got to use this algorithm is this work by Azat, very good colleague of Dr. Troshin. And basically, he used a lot of different methods to put zinc, to manufacture zinc oxide. And the whole result that's most important to us is we have zinc oxide, and the best one is when it's passivated with an H2. And it's passivated a lot with an H2. The other ones are not as good. And the whole goal of theory was to determine why is that, to answer the question, why is that? So, first of all, before we do anything else, we need to get a stable interface. So typical values of the interface binding energy is from 2/10 to 1.2 joules per meter squared. This is a very well studied topic actually. Many people have already studied it, so it's a bit tough to get into it. Generally, they get 5 to 10% mismatch, and when we look at our numbers, we get less than 1% mismatch. So the two interfaces we proposed are superior to the ones known in literature. And we see that we can interface with both gamma-MAPI and alpha-MAPI. And also the blue box indicates we have slowing off of PBI2. PBI2 cannot, of course, degrade under light further. It's a big problem. And this just indicates that we also have a chemical problem, not just a mismatching problem, we have a chemical problem. What is the chemical problem? The chemical problem is zinc oxide surface is amphoteric. When you mix it with perovskite, it's basic. And when you look at the DFT tells the story perfectly. Our MAPI, methyl ammonium itself, gives away its hydrogen to the zinc oxide, and you can see it right there. That's the problem, and it always happens if you launch this calculation this way. it's reproducible. Okay, so that's where Azad's experiment comes in. When you put a little bit of NH2 on the surface of the zinc oxide, it's no good. We actually lose dimensionality in the MAPI. That's really bad. If we use plenty of NH2, we can see we get a really nice interface. The interstitial binding energy is simply great, and the mismatch is below 1%. So this is a very good interface. And you can see that also we have like a mixture of cubic phase and zinc blend. This is normal. At room temperature, zinc oxide does this. It's just known. And in the experiments also, mixture of phases. That's another thing that made things a little bit harder, is that we have to consider not very many, but many zinc oxide phases. So yeah, when we look at this, we did our due diligence and did a 25 picosecond molecular dynamics run, which confirms completely that this interface is stable in time. And so we know for sure no more hydrogens transferring over, and that's the explanation. So that's pretty much it. You can see this remains stable over time. Okay, and this is a very exciting topic, self-assembling monolayers and coSAMs, SAMs and coSAMs. So we took our SAM and then we also mixed something else into it. Okay, and here I'll mostly focus on the calculations. But basically, experiment took, the thing we're interested about in experiments is, so they took, the one we chose was PFPACl and NP-TMS, and the head here is pretty big because it's silicon-based head, and these are carbon-based heads. And then the tail is always SH. And also this silicon-based one can also hydrolyze, so these CH3 groups can become OH groups or just oxygen groups. And the one we chose was OH group, so the intermediate phase. So the thing to think about here is previously in very good papers, they were also interested in thinking about the coSAM problem. So they just tried to coat the surface with just the SAM, and then they added the coSAM. These are DFT calculations. These are LAMPS calculations. These are force field-based calculations. So basically, they didn't really, their way of doing this did not actually achieve a monolayer. So they added the coSAM and they get sort of covering, but visually it seems like it's not enough material. But what turns out to be the problem is if you try to do this by hand, it aggregates, the SAM aggregates. So you need a lot of SAM to get coverage. And a lot of SAM is actually what the case is in experiment. And experimental guidance helped us here a lot. So we take PFPACl and NP-TMS with the hydrolyzed tails. A lot of work had to be done to launch this in the LAMPS. LAMPS is not very easy to work with, so we had to go through a whole process and wrote the code, and we put it on GitHub so other people can reproduce it for other materials. But basically, the whole idea here is we need to train a bunch of force field coefficients, both for the passivators and the nickel oxide. We also had to modify to be compatible with these. So there's also a compatibility problem. Anyways, once that was all done, basically we populate this space above with our SAM, and then we actually have an application process, just like an experiment, right? It's you press down with the perovskite, so we press down a wall on the SAM, and that way we get a realistic case where the SAM actually formed the film, like in real life. So that's just the PFPACl. Then when we mix it with NP-TMS, you can see the behavior is quite different. It clumps up a lot harder and a lot denser. So you get a denser film. And if we double the NP-TMS, we get even stronger clumping actually. So we get a really dense material. So this is all done via moving wall potential. Not many people have done this before, so we're kind of first on this almost. And then after that application process is done, after the initial commotion, we can see that the film is pretty much immobile. It is as it is. It just sits there, which is good. We don't want liquid like film. Okay, so here's the surfaces we get. These are averaged in time. So with just PFPACl, you can see we have holes here. So it aggregates way too much, and we end up getting these holes in the material. So that means the perovskite and the nickel oxide can touch, and that's no good. And then for the mixed material, if we add a little bit of FPTMS, we get an improvement, and then we add a lot of FPTMS, the improvement is even more noticeable. And then we did this before the IR experiments. This actually reproduces very well. So this is basically a heterogeneous kind of film that comes out. So we have PFPACl and PTMS not mixing, but kind of forming separate phases. And that's actually what, if you imagine the red being blue, we can compare them, and that's actually what we see in the experiment. So this was done after our simulations. So the simulations predicted the experiment, and that's the golden standard, I think, for theory, if they can predict something new before it's done. So final section is about the neutral passivators. So this is the only paper that's unpublished. So the whole thing Luba wants to do is stabilize the inorganic perovskite. It has a lot of advantages, but it's phase unstable, so it degrades the yellow phase very easily. So how do we stabilize it? The idea was cytosine, and basically when you add cytosine, the experiment does find that the inorganic perovskite starts becoming more stable. So for cytosine, we use this topological analysis of the molecular electrostatic surface potential, so the critical points. The critical points are where we have the most negative charge. So you can see for the monomer, it's just here, a little bit on top. And for the dimer, we can see that it's much more homogeneous, so it's all over. So what we think is that it actually starts blocking the binding movement when it dimerizes. You can also see the lithium affinity number goes up, so the basicity goes up. This is the surface interaction, so you can see the monomer can just stick on the surface like this, and the dimer has a much more complicated interaction. So basically the dimerization competes with the interaction of cesium. That's interesting. And yeah, we did our due diligence, so we took the dimer and we just went through all the surfaces that we see in XRD. 002, 004, 100, 200, and so on. And you can see the absorption energies are pretty good for a neutral passivator. There's the electrostatic surface potentials. Again, we did all the everything that's done XRD we did, and this is rarely done, so we did our due diligence, so a lot of work. The really cool thing is we thought about it and we proposed something theoretically, is we could make this kind of paper clip of 2 dimers of cytosine. They make this paper clip that can actually grab hold of 2 perovskite grains and hold them together. And when we calculate the interstitial binding energy, it's very strong actually, because remember the PE, the 2D phases based on PEA are like 3 or 4 times smaller than this. So this will create a very strong binding between the grains. That's interesting. So that's something we need to investigate. Okay, this is the final topic. Melamine is related to cytosine because it's kind of similar. So melamine is meant to, sorry, the name got blocked out here. It said Loa. And so yeah, the whole thing here is it passivates the PBI2, that was the goal. And yeah, DFT showed that in agreement with experiments, the PBI2 is actually passivated better than the surface. So yeah, that's in the present in the case so the PBI2 coexists with a perovskite and is passivated better. And we also believe it might serve as some kind of vertical liner, because a lot of literature nowadays says that when we have 2D phase or PBI2, the charge transfer is better if the 2D phase or the PBI2 maybe is aligned vertically compared to the perovskite surface. So perovskite surface is horizontal, and then 2D is aligned this way. Because often you see it aligned this way, horizontal, that's not good. For charge to transfer easily, you want a vertical. That's another engineering problem to think about. Let's just shortly look at the IR snows because they are super cool. And the thing about them is, so when we look at the MA and FA distribution, you can see that the MA and FA segregate. So that's kind of unusual. We generally don't think that they segregate, but they do segregate. So black phase is also segregated. So the problem is very complicated. They localize in different places. And then we have MEA right here. And this is the perovskite surface, by the way. So yeah, they add PBI2 plus MEA, and we can see the MEA also kind of localizes in clumps. And then when we add cesium iodide, the clumps are a little bit different, a little bit smaller, but they don't see any other evidence that the passivation gets worse. So they concluded that there must be some kind of invisible phase. And DFT gives an explanation. So yeah, experiment says there must be an invisible phase. When we look at their chosen phonon frequency 1525, similarly as 1527 DFT, so very, very close result. Yeah, so we predict that this phonon frequency is super weak for the monomer. As it dimerizes, we see a strengthening mode nearby, 1545. Possibly this error in DFT, maybe it should be 1525. But anyways, it's small for the dimer, then for the tetramer, it's very strong. So we get this model, monomer invisible, dimer semi-visible, tetramer and above visible. So as the symmetry breaks more and more, we see it more and more in IR. So that's a super cool result that we got here. Yeah, so that's the result. And so yeah, I'm finished. Here are the works completed. So impressive amount of work done in 9 months. I think we did it together. Great job to everyone. All published in Q1, only one in Q2. Meanwhile, I also continue my collaboration with Troshin group, and also we did some work together. So that process is also going. Pavel is also collaborating with Dr. Xu, so we have a grant together, so everyone is collaborating together. The conclusions I want to just say, these are going to be short. Interfaces are quite challenging to build in a rational way. They either have high mismatch or chemical instability, so they are tough to build. For passivation, the problem is also complex. There's many IDs and methods. There are constantly new IDs coming out. For DFT comparisons, we need some kind of standardization because as it turns out, I can only compare my own results. So I just take my own papers and compare them. When I start looking at literature, tough to do, no standardization. And also often mistakes. That's the big problem. Yeah, so thermodynamic and electronic properties can be calculated. There are a lot of caveats. More work is required as always, which is good. Which is good and bad dialectically. So yeah, thank you for your attention, and I will be accepting questions.
Any questions?
They say there's no stupid questions. I know you're all experimentalists.
Probably lots of questions. Any questions? Actually, I have a lot of questions.
Yeah, go ahead.
But, yeah.
Okay. I have a question. Because you are focused on the DFT, but now that has high slope limit and network to calculate or summarize the net area or passivator
AI.
But do you think this will change the way we think about the materials, or maybe we make a PFT supplement method or something?
Yeah. So high throughput methods, definitely, it's definitely, right now I kind of already use a high throughput method. It's just, I didn't present it here, it's going to be for next time. So the non-adiabatic molecular dynamics requires high throughput because you have to do 2,000 separate calculations all in a row, then combine them. So we already do high throughput. But I think the other thing is AI prediction, right? So can we use AI for our research? Yeah, I use AI for my research. I use ChatGPT a lot to guide my research. I use it a lot to help write programs, so it's already kind of built into my work process. For machine learning, I'm also interested. There's a problem I'm working on right now where machine learning will be useful. But specifically for passivators, it's actually funny. There's a recent paper which just used a language learning model, so it doesn't even know anything about chemistry. It just goes through all the papers, looks at other materials where passivation was successful, and just predicts the best passivator without knowing anything about chemistry. So yeah, to answer your question, yes, it will be useful even if it doesn't know much chemistry. That's interesting.
再提一个问题。
I have a question. In one slide, you have mentioned that there was iodide in the interface. You said iodide makes the work function low. It is not good for the interface.
Which slide is it? Was it in the middle or the end?
Yeah, it was in the middle. Here you mentioned.
Okay, at the very start. Yeah, that one's. One second, let me go all the way back here. Sorry, the presentation was so long that it takes a bit of time. I've never actually done a 1 hour presentation. So this is an interesting experience.
Yeah, this one.
Oh, yeah. Sorry.
This one. You say iodide is.
Yeah, well, it's not just I said it, they said it. It's not my claim, it's their claim. Yeah, it's so weird. So it's hard to explain because they say it's because the tosylate and the octylamine counteract each other in terms of dipole moments. But when you think about it, when you take octylamine, positively charged, and iodine, you now have a new dipole interaction.
Yeah.
So canceling each other seems weird. What I think is going on is that when you add iodine, and I've seen this I don't know about this case, but I've seen this for TFP and PFP. So if you add TFP by itself, the dipole will go this way. If you add iodine, the dipole will start going this way. And when the dipole turns around, what you have now is a dipole that's pushing the electron into the material. And then, in our case, maybe instead of the plus, we push through a negative charge. And that might be what's making it better. But this will require experimental investigation. This is just a theoretical prediction. So why is that? Hard to say. In their case, it's bad. In our case, maybe it's not bad because our case is different. It's a fluorinated case.
But only with the HDL, not ETL.
Yeah. So we're talking about just. So yeah, we have to keep our polarity in mind. So if we have a PIN device, it should work. For an NIP device, it's probably the other way around. So maybe for the NIP device, if we can get this same thing going, it's actually good, right? So if we just switch, if we have now an NIP device, do the same kind of passivation, maybe it'll actually be a good thing.
Yeah.
Who knows? So I think this experiment is actually super useful, probably, just to see how charge localized. So maybe more experimentalists should use it. I don't know how hard it is to use, but if it's possible, I think it should be implemented more. Because for me, it's very useful.
Because chlorine Cl is okay for the interface, I think so. And I was just curious why iodide is not.
It's good. I think for each case it'll be different. Like the problem is, it's so hard to generalize anything in this field. Every case is a separate case because I mean all the topics I discussed, you can see they're kind of different each time. It's hard to generalize.
Thank you.
Yeah, it's for NIP.
Yeah.
NIP structure.
Yeah.
Yeah.
Is it an NIP?
With HDL, spiral.
Spiral. NIP structure.
Oh, it's NIP structure?
Yeah.
Okay, it's the other way around. Yeah, but still my logic applies because they're getting plus charge at the SnO2 interface. And that should not be happening. It should be probably should be the other way around. Sorry, I mixed it up.